at the very beginning of this semester, we talked about sampling, right? And we say we sample xn using period t, and this is what happened, right? For example, t is equal to 1, then this xn, we will just get 1 sample, 2 sample, 3 sample, and like this, okay? So this will be the samples that we get. If t is equal to 1, then we take sample from 0, 1, 2, 3 like this. 0, 1, 2, 3, this is xn, okay? Oh, this looks a little bit uneven, doesn't it? Let me redraw this so it looks a little bit nicer. 3, okay. Now, if we sample faster, so the sampling period is smaller, then what do we have here? These are the yellow one. And now if we sample faster, let's say t is equal to half, then we also get half integer point. All right? So the picture would look like this. 0, 1, 2, 3, 4, 5, 6. All right? And then we get the yellow and also the blue. Well, in this particular example, the spacing is a little bit different. In this figure, we have 2 to 3. There's 1, right? This big. And in here, 2 to 3 is like this big. Does it matter what the spacing are? Does it matter what the spacing? Here is like this big and here's like this big. Does it matter at all? No, it doesn't matter, right? The important thing is the index. This is 0, this is 1, this is 2. Okay, this doesn't really matter. And when we take this as samples, we call this C to D converter. This is called continuous to discrete time C to D converter. Okay. The input of the converter is continuous time signal XC, and the output is samples of XC, C to D. And we often put, because this output really depends on the sampling period that we have chosen, so very important here is a T. We don't just have a C to D, we need to know the sampling period, then we know what's in this C to D. Alright? And this T is what we call sampling period. And sometimes we use this quantity as well. This is called sampling frequency. Sampling frequency, 2 pi over t. It has this radian frequency, 2 pi over here. Radian frequency 2 pi, so this is angular frequency, so it has a frequency here. But actually, when you talked about sampling, you may see sampling elsewhere. Usually there's a parameter. They don't say sampling period or sampling frequency, they say something else. When we talked about sampling, there's usually a parameter that we refer to when we talked about sampling. Yes, thank you. Sampling rate. And sampling rate is simply 1 over t. These two may be a little bit confusing, but if you want to remember the name, just remember that this has a 2 pi. This is a 2 pi. So this is called frequency. Okay, sampling frequency. And this is sampling rate, is 1 over t. So it tells you how fast it samples. So this is the sampling rate. Now this whole chapter is about sampling. Chapter 4 is about sampling. Why do we do sampling? Any reason why sampling is very important? Why you think sampling is relevant? Oh, thank you. Very, very important. Most signal processing are done digitally. That's what you meant, right? Signal processing are done digitally. Okay, any other reason? That's as far as computation is concerned. Because most signal processing, we do it on using computer, so we need to do sampling before we do the processing, right? Any other reason? Storage problem. Because almost all signals are stored digitally. Oh, I'm sorry. I think what I've been writing is slightly different from what you're saying. You're saying that because we want to do data compression. We want to reduce the amount of storage, so we do it digitally. Yes, that's true. That too, yes. Because most of the signals are stored digitally. Why they are stored digitally? Because of what you said. Because we want to reduce the space, the storage space. Okay, how about some examples? How about some example with sampling? For example, well, when is the time that you use sampling most often? When do you use sampling? Well, actually, we use sampling almost every day. Well, now not that we are sampling the signal ourselves, but we have some things to sample the signal for us, right? So, any example? We have so many gadgets these days. Products. Any product that we use every day that does the sampling for us? Well, actually, you know what? Almost all of us use some device to do sampling for us every day. What is the thing they use the most often? What is the device they use the most often every day? Mobile phone, yes. Do you talk on the phone? Well, don't tell me you don't talk on the phone anymore. Well, you talk on the phone. Then your mobile phone is doing sampling for us. Okay. So you talk on the phone, yes, and it does sample, yes, like this, right? How fast does it sample? Your voice. Because when you talk on the phone, it's your voice that's sampling, right? So how fast is it sampling? Oh well, this one maybe not everybody knows, huh? Mobile phone. All right, how about another one that you might be more familiar with? How about CD? CD. Everybody listen to CD, right? Oh no, nobody listen to CD anymore. Everybody listening to MP3. Okay, so anybody knows how fast a CD is sampling? How about DVD? All right, forget about voice. How about video? How fast is video sampled? Oh, no idea. Okay, I think this one is more probable. Well, this one, usually we sample with a mobile phone. We sample at 8 kHz. 8 kHz. So that's fs. Sampling rate is 8 kHz. That means for every second, 8,000 samples are taken. That means 8,000 samples per second. Okay, that's a mobile phone. How about CD? Do you think it's going to be faster or slower than 8 kHz? Faster. Yes, indeed. It's a 44.1 kHz. And DVD, well, DVD is a little higher too, 48. So for different signal, we have different sampling rate. Why do we need a different sampling rate? For quality, that's very good. That's very good. You mean you want to keep the original, is it? That's because you want to keep the original. Okay. So that brings us to the very important question of reconstruction. For reconstruction. Because we don't just samples. We don't just take those samples so that the signal can sit in our computer forever, right? We want to use it sometime later. For example, if we sample our voice, we want to send our voice out to somebody else so that another person can hear it, right? So for reconstruction, like you said, if we sample, we use different sampling rate because we want quality, right? So for reconstruction purpose, how would we like T to be? We want to be the bigger the better or the smaller the better, or FS? The larger FS, the better, right? For better quality, the larger FS, the better. For reconstruction, the larger sampling rate is, the better. But how about for storage? For storage purpose, how would we like the sampling frequency or sampling rate to be? We want it to be as big as possible or as small as possible? As small as possible. So the smaller the better. The smaller FS, the better. So this is kind of contradicting, right? For reconstruction purpose, we would like FS to be as large as possible. For storage, we would like it to be as small as possible. So how to choose? How to choose a proper FS, or how to choose a proper T. So that brings us to the very important question, how to choose T. And what's our goal? We would like to choose T. T should be as large as possible, right? As large as possible. So that there's one condition, right? We don't just want to choose a large T without consideration of reconstruction. We still want to reconstruct the signal such that XCT can be reconstructed from the samples. So that's our goal. So let's answer this question in two aspects. So first one, we would like to know when we sample what happened. We know perfectly well what happened in the time domain, right? We know what happened in the time domain, right? But to analyze how XC and X are related, what do you think would be a more useful approach? In the time domain or in the frequency domain? Oh well, that brings us to another question about this is all different sampling schemes. For mobile phone, it's 8 kHz. For CD, it's 44.1. Of course, CD has a higher quality, but one very important aspect are this is for mobile phone application, this is for CD application, right? There is some difference in the nature of the signal, not just about quality. There's some difference in nature. What would be a very important difference between speech, this is what we call speech, right? You're talking your own voice, and signals on CD. CD, usually you have music on the CD, right? What would be a very important difference? Like he said, when we speak, I speak like this, right? That's as far as I can go in terms of a high pitch, high frequency. But with music on CD, do you think it can go higher? it can usually go much higher, right, than human voices. So there's a difference in signals in terms of the frequency. And that's why we are sampling, that's one very important reason why we are sampling using different sampling frequency. All right. So which one do you think would be a better tool for analyzing, in time domain or in frequency domain? Frequency domain, right? We're always talking about frequency. So frequency domain seems to be a natural choice. So we would like to know, we already know how they are related in time domain. We would like to know how are xej omega and xcj omega related. And as far as the reconstruction is concerned, then we would have a D to C converter that convert discrete time sequence to continuous time signal. Okay. So we would like to know how are xrj omega and xej omega related. Okay, and then we will know when we can have xr equal to xc. Okay. To talk about how these two are related, let's use a conceptual representation. Conceptual representation of C2D. Okay? This is C2D has two blocks. This is C2D has just C2D, right? But we are going to look at it as if it's the cascade of two blocks. This is impulse train to discrete time sequence. Xn. Okay. And this S of t is given like so. It's a impulse train. It's an impulse train. Okay. The action of taking samples, we are going to look at it as if it's implemented in two blocks like this. First, it's multiplied with a signal called st, and then we have an impulse train to discrete time sequence. All right, let's explain each one separately. So first one, this S is an impulse train. So let's say we have, suppose this is our xct. Okay, this is xct. And S of t is an impulse train. You see, it has an impulse every t seconds. Okay, this is a t. Okay, so if we write it down, it's like an impulse t plus impulse t minus t, all the way like so. And on the other side as well, delta t plus t, like this. Okay. I just wrote down three terms, all right, but they are infinitely many terms. So st would look like this. It has an impulse at 0, and at t, at 2t, 3t, every t second it has an impulse. So let's draw S. Has an impulse, 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 like so. It's a continuous time signal, okay? It's a continuous time signal, so we are drawing continuous impulse here, okay? So this one is delta ct minus t, like so. Okay. And the output of this multiplication expression here. Let's say it's xst. xst. All right. So now let me ask you a question. When we multiply an impulse with a signal, what's going to happen? What will be the result? What will be the result when we multiply an impulse with a signal? Let's say we have a signal here, and we have an impulse here. We have an impulse here, delta c t at 0. And what's going to happen? We multiply these two together. What do we get? Yes, we get an impulse, right? We get an impulse. But then this impulse will carry the value of which point of xct? It will carry the value of xct at time equal to 0, right? So when we multiply this impulse with this signal, what we get here is an impulse, and it carries the value of xc at time equal to 0. And now when you multiply this impulse with xct again, then we get another impulse, but this time it's going to carry the value of xc at time equal to t. So here's another impulse, and this is going to be xct, like so. Okay? So we still get, this is an impulse train. This is an impulse train. This is what we call an impulse train. 就是一连串的这样子的 impulse， 我们叫 impulse train， 就是这两个字哦 ，impulse train. But when we multiply these together, we still get an impulse train, but each impulse will carry different value, right? And those values are the value of xc at the point that we want to sample, right? So this is s of t. It's a continuous time signal, and it's full of impulse. It's an impulse train, like this, okay? 0, t, 2t, 3t, okay? S of t is non-zero only at integer multiple of t, and it's 0 at everywhere else. And then xn. For xn, we simply convert the value that each impulse carry to a sample. Okay, so this one, it will be a sample. Now we don't have this arrow anymore because it's a sequence, and this is just a sample. And for this one, this is xc0, and for this is 0 and 1. For x1, we simply take this impulse, we take the value that the impulse carry and convert it to a sample. So this is xct. Is it okay? 所以我们呢考虑的是说，我们把 xc 这样子一个 continuous time 的一个讯号呢，我们把它去取 sample， 每大 t 的时间呢，我们就去取 sample。每大 t 的时间我们就去取 sample， 那就等于是呢，我去取了 sample 之后，它就对应到一个 sample。我去取这里的值，然后对应到这个 sample， 取这里的值，然后去对应到这个 sample。所以本来 C to D 的话，就是从这里呢直接跳到这里来了 ，OK， 直接跳到这里来。那跳到这里来的话呢，这个当然没有问题。可是我们如果去想要知道说，它们 frequency 里面发生了什么事情的话呢，我们可以把 C to D converter 呢想象成它是由这两个去串起来的。那这个是第一个部分，这是第二个部分。这个叫做 A 好了，这个叫做 B 好了。OK， 那实际上的 implementation 呢，我不一定要这样子做。我可能不一定要这样子做，我才可以得到这个 C to D converter。可是呢，我这样子做的话呢，我可以想象说它是这样子做，那这时候我可以比较的容易就去看到说它们 frequency 里面发生了什么事情。那因为是 sample 的关系哦，大家看一下这是 sample， 所以实际上它中间的呢全部都丢掉了。它中间的值 xc 这从0到t这里面有无限多个值，这些值呢全部都丢掉了。 那我们如果想要去从数学的角度去把它描述出来，因为我们想要知道说，他们是什么关系嘛，对不对？我们想要知道他们什么关系，所以我们要去把它描述出来的话呢，那我们可以用这样子的一个 impulse train， 因为这个 impulse train 呢，它就是只有在 t 的倍数的时候呢，它才会有值，所以它去跟它相乘的时候呢，就可以把 xc 在 t 的倍数的那些值呢，去把它抓出来了。那抓出来藏在哪里呢？就藏在每一个 impulse 它所带的那个值上面。然后接着下来呢，我们再把这每一个 impulse 所带的值呢，去转换成每一个 sample。那这样子我们就有我们的 xn 了。我们这边的话呢，我们可以去做推导哦，就是把 xc 到 xs 它们之间的 Fourier transform 的关系去把它找出来，就是 a 的部分跟，然后接着下来呢，从 xst 它的 Fourier transform 跟最后的这个 xn 它的 Fourier transform 的关系去把它找出来，就是这个 b 的这个部分。那这个部分的推导的话呢，大家可以在 video 里面看到，但是我可以先把这个结果写下来。So first of all, we have A. Let me write down A. For A, this is what happened. XS is still a continuous time signal, right? So when we look at this Fourier transform, we say J big omega. That's usually the notation you use for Fourier transform of continuous time signal, right? J and big omega. Okay. Well, it doesn't matter if it's not. XSJ omega, how is it related to XSJ omega? How is it related to XC? It's related like this. This is XCJ, and then omega minus k 2 pi over t. And for all k, this is for all k. Okay, so that's how the first two, these two signals are related. A, just for A. This is signal Fourier transform, and this is signal Fourier transform, how they are related in Fourier transform. Okay? And then B, let's write down the result and we will talk about what this means. B is XEJ omega, all right? Now we write exponential J omega because X is a discrete time sequence. X is a discrete time sequence, so the Fourier transform is XEJ omega. Okay, so very, very important, XCJ omega. One is XCJ omega, and the other one is XEJ omega. This is the Fourier transform for the continuous time signal, and this is the Fourier transform for the discrete time signal. All right. And XEJ omega is related to XS like so, J omega over T, like this. So just a change of variable. For the second one, it's just a change of variable. So as far as you can see, this one seems to be a smaller expression and it's easier to understand, right? It's just a change of variable. So in terms of Fourier transform, this is going to be just a squeezing or stretching, right? In terms of axis, in terms of picture. Because there's a scaling of t, right? So you simply stretch it or squeeze it so that this, from the picture of xs, you can very easily get the picture of x. Is everybody with me? 我们在这里看到的是一个，就是只是把它除上 t 嘛，对不对？好，除上 t 的话，那就是一个那个 scaling 嘛。可是现在是一个轴的 scaling。如果是一个轴的 scaling 的话，就好像 x 的 2t 或者是 x 的1/2t。这个 x2t 的话，那就是把原来 xc 的那个图形，你把它压到原来的1/2，就把它压进来嘛，对不对？就是 squeeze。那另外这个的话，就只是把它拉开来而已嘛，只是把轴拉开来而已。所以说，如果我想要从这个 xs 的话呢，我就很容易就可以得到 x 了，因为这只是一个轴的那个 scaling 而已。OK， 那这个的话看起来比较大一点，对不对？所以我们来看一下这个 xs。 How is xs and xc related? xs, well, if we write it out, this is what happened. Let's write out all the terms together. This 1 over t is just a scaling. So let's forget it just now. Let's look at the summation. This summation has infinitely many terms, right? And remember 2 pi over t is what we call sampling frequency. Yes, that's omega s, right? So let me write omega s. And we have infinite many terms here. For each k, we have a term here. So let's first write down the term that k is equal to 0. xc j omega. That's easy. And the term that k is equal to 1. Then we get j omega minus what? K equal to 1. Then we will get minus 2 pi over t, right? K equal to 1. Then that's omega s. This is k equal to 1, right? And continue on. K equal to 2. Omega minus 2 times omega s. And all the way to k equal to infinity. And on the other end, we have k equal to minus 1. Then we get xcj omega plus omega s, right? Like so. And we continue on that side as well. All right, so it's a huge summation, right? Now let's use one example to see. Let's say that xc is a signal like this. This is xc 0, omega 0. Okay, this is xc, all right? And for such a signal, we say it's band limited. Band limited. Band limited. Omega to omega less than omega 0. Because if we look at the Fourier transform, it could be non-zero between minus omega 0 to omega 0, but beyond these two, beyond omega 0, they're all 0. Okay? It's 0 here, and it's 0 here. Okay, so it's band limited. All right, let's use this example and draw xs. What would xs look like for this example? This is omega, and this is 0. What would xs look like? For xs, it has how many copies of xc? It has many copies of xc, right? It has xc right here. So let's draw this copy first. It will be right here. All right, and this is omega 0 minus omega 0. And the height will be scaled by this one. And then there is a shift of xc, shifted by omega s. Okay, so now let's look at two cases. Let's say in this case that omega s is larger or equal to 2 times omega 0. Okay, omega s is larger or equal to 2 times omega 0. All right, and let's say omega s is here. Let's say this is omega s, okay? And then, because it's larger than 2 times omega 0, right? Larger than this width. So let's say it's this copy is right here. Is that okay? And this is xcj omega minus omega s. And we continue on like this. So there will be one copy at omega s, another copy at 2 omega s, another copy at 3 omega s, continuing on and on and on and like this, all right? And how about the other end, the other side? Do we have something on the other side as well? We do, right? Because we have plus omega s. So there's going to be another copy at plus omega s. Let's say this is white, so it's going to be right here. This is minus omega s. And this is the copy xcj omega plus omega s. So it's going to continue on this side as well, on and on and on and on. Right? So how about xej omega now? How about xej omega now? Remember from xsj omega to xej omega, it's simply a frequency scaling, right? Right. So at 0, it corresponds to 0, right? And let's say 2 pi. Say omega equal to 2 pi. Omega equal to 2 pi. Right? Because remember xej omega is periodic, right? Xej omega is periodic. From xs to xej omega is simply a scaling, a frequency scaling. If x is periodic, x is periodic with a period of 2 pi, right? Then xs, should it be periodic? Xs, it should be periodic as well, right? If it's not periodic, then we are ruined, okay? It should be periodic as well, right? So let's say, which of these frequency will correspond to 2 pi? Well, we'll plug in omega equal to 2 pi and then see what happens. Ej 2 pi, xsj 2 pi over t, and that would be 2 pi over t. 2 pi over t is omega s, yes. And that's what this is, omega s. So 2 pi, so right here we would have, this point will come here, 2 pi, right? And omega 0, what would be omega 0 then? I'm sorry, this is omega 0, and what would be this point? Oh well, this is a 2 pi over t, right? 2 pi over t, right? So it sounds like it should be a multiplication of t, right? So this is omega 0 and t, all right? And this is minus omega 0 and t, all right? So now it all fits in together. Xej omega is a periodic 2 pi, and indeed this xs is periodic with the period omega s. Right? Now, just now we used the example that omega s is 2 times omega 0, larger than 2 times omega 0. Now let's try another example when omega s is less than 2 omega 0. Okay? We would have the same example. Let's draw xj omega and xej omega. Okay. Xs is still related to xc like so. So first you would have a copy corresponding to k equal to 0. This is xcj omega, 1 over t. Oh, here they all should have the scalar 1 over t. Yes, 1 over t and 1 over t. Okay. 1 over t xcj omega, and then there's going to be another copy at omega s. But this time omega s is not larger than 2 times omega 0, right? So let's say omega s is right here. This is a half. So this is not 2 times this one, right? It's not the width of this one. So it's not big enough. So when we have the another copy, the other copy, xcj omega minus omega s. It's going to come right here. Okay. Now there's going to be some overlap because there's not enough space. And when we add up all these, remember xc is a summation of all these different copies, right? So all these different copies will get added up. Then what do we have? From here to here, we still get the original value of xc, right, with the scalar. And here we also get the original value of xc. But right in the middle, there's overlapping between two copies, and we wouldn't know what the original value of xc is, right? And when we draw, this is what we have. This is one period from minus pi to pi of xcj omega. This is 1 over t, this is 1 over t. Oh, and the height is the same, 1 over t. And whenever there's overlapping, whenever overlapping occurs, we say there's aliasing. And this is due to aliasing as well, this part. We say there's aliasing. And if we look at this case, then we can see that although the height is smaller, but that doesn't really matter. If we just look at this part, then it has an exact copy of xc. Although there's some frequency scaling and there's scaling in height, but still, if we just know this, if I tell you what this is, do we know what the original xc is? We should be able to get back xc, right? And so in the video, we will talk about reconstruction. In this particular case, we will be able to reconstruct the original continuous time signal, if this is true. And let me write down what I just said here. For omega s larger or equal to omega 0, xej omega is a copy of xcj omega, albeit with the frequency scaling. And for this period, if we just look at a 2 pi period from minus pi to pi, for omega in minus pi to pi, xej omega is simply x. This is xcj omega, right? So this is a frequency scaled version of xcj omega. A frequency scaled version of xcj omega. So it's simply a frequency scaled version of xc. Okay. If this is satisfied. And in this particular case, we will be able to reconstruct